Thank you, Shen. If you have any question for them, you can also put on Slido and they can reply later. Now the next presentation for the day will be themed Accelerating the Surrogate Retraining for Poisoning Attacks Against Recommender System by Yunfan and team.
Hi everyone, I'm Yunfan Wu from the Key Laboratory of AI Safety at the Institute of Computing Technology, Chinese Academy of Sciences. It is an honor to be here at RecSys 2024 presenting our work on accelerating the surrogate retraining for poisoning attacks against recommender systems. Here is an overview of what we will cover today. We will start with some background and then dive into the analysis of our proposed method and the specific strategy. And finally, we will look at our experimental results and conclude the work. Let's begin with the brief overview of recommender systems. These systems are frequently deployed in our daily lives, influencing the decision-making process and the behavior of users. However, these recommender systems are vulnerable to attacks. They can be manipulated by what we call poisoning attacks. In practical scenarios, these attacks are often carried out by injecting users into the systems. In this example, we can see attacks that are in the attacks, a normal user who has purchased pizza and beer and an injected fake user has also bought the two items with the normal user, but the fake user also bought a harmful product, and the recommender system could potentially be manipulated by the injected fake user and recommend this harmful product to the normal user based on the similarity of their purchasing pattern. This manipulation can lead to user receiving potentially harmful or unwanted product recommendations, compromising the integrity of the system. Okay. Data poisoning attacks have been widely researched in this area, and the attack procedure typically involves attacker injecting fake users into the recommender systems, and then the system is retrained on the poisoned dataset, leading to manipulated recommendations for normal users. Here you can see the mathematical formulation of the problem. We formulated the problem as a binary optimization. The inner optimization is the training of recommender systems, while the outer optimization focuses on the fake users. Here, theta represents the recommender parameters, while IR are the interaction data of real users, and IF are the fake users. Poisoning attacks against recommender systems have evolved from simple heuristic methods to more sophisticated optimization-based methods. This slide shows the general framework of optimization-based attacks. It involves an iterative process of continuously optimizing fake users to maximize the attack effectiveness. A crucial step in this process is surrogate retraining. As shown in this figure, after each update of fake users, the surrogate recommender has to be retrained on the pointed dataset with the latest fake user profiles to evaluate their attack effectiveness and guide the optimization of the next step. This repetitive surrogate retraining is particularly time-consuming. To illustrate how time-consuming this process is, this figure shows the time consumed by 3 existing attack methods. As you can see, the surrogate retraining takes up a significant portion of the total attack time consumed. For example, conducting DPA to DL attack on a large dataset turn can take over 10 hours, while the surrogate retraining accounting for more than 80% of this time. The time-consuming nature of surrogate retraining severely limits the attack efficiency, especially for large-scale recommender systems. This challenge motivates us to accelerate the surrogate retraining process without compromising the attack effectiveness. To address this, we propose our method, gradient passing, based on both intuitive insights and theoretical analysis. It aims to accelerate surrogate training while enhancing poisoning attacks. Now let's move on to our analysis of our proposed method, gradient passing. To understand our approach, it is important to recognize that training collaborative filtering models is essentially a representation learning process. In this process, user and item representations are adjusted to reflect their preference and features. Positive interactions bring representations closer, while negative ones push them apart. In this example of one optimization iteration, user 2 and item 1 form positive pairs, while user 2 and item 1 are a negative sample. This causes user 2 to be optimized towards the bottom left corner in the representation space. However, this optimization direction moves user 2 far away from item 2, which also is a positive pair for the user 2. In subsequent iterations, item 2 will also be optimized to the bottom left corner to maintain high similarity with user 2. This describes a cascading effect, where in this cascading effect, a user's representation moves, causing the items they interact with to also adjust move with the user. The rightmost state shows the final convergence state, where item 2 is in the bottom left corner, the same as the user 2. To accelerate this training process, we propose gradient passing. It explicitly passes gradient between interacted user item pairs, as illustrated here. GP directly passes user 2's gradient to item 2 and brings it to the bottom left corner within one optimization iteration. GP can approximate the cascading effect that occur over multiple original iterations, thereby accelerating the convergence of recommenders. These slides compare the original training with GP. We can see that GP optimized item 2 to a position closer to the convergence state. It allows for faster propagation of information through the system, accelerating the convergence of surrogate retraining. We have also conducted a theoretical analysis of our method. We proved that a single training iteration using the past gradient can achieve the effect of 2 iterations with the original gradients. Theoretically, we found that the ideal GP matrix shown in this equation. While it is impractical to directly apply this AGP matrix, practically it provides the vulnerable guidance for our practical approach. The key insights we drive are: first, the matrix consists of 3 distinct terms with different weights, and the second term facilitates GP between user item pairs, and the third term enables GP within user pairs and item pairs. These insights form the foundation of our practical GP strategy. Now, let's dive into our GP strategy. Inspired by method passing GNN, we apply multiple gradient passing layers. Our theoretical analysis shows that the odd and even GP layers play different roles. So we set different GP metrics for odd and even layers, and the final modified gradients have different contributions weights from odd and even layers. These slides show how we define the gradient passing matrix for the even layers. It passes gradient between interacted user item pairs and use a condition term to select those pairs exhibiting a similarity reduction in current optimization iteration. We then implement multi-layer gradient passing using a normalized passing matrix and collect the results of the passed gradients from the even layers, that is 2, 4, 6 layers. For odd layers, we construct the gradient passing matrix similarly and collect the passed gradient from the odd layers. The final modified gradients are sum of the original gradient and the passed gradient from both odd and even layers with different weights. The only distinguish between even and odd layers lies in their different threshold and different weights. Now, let's look at the experimental results. We conduct the experiments on 3 datasets and 5 victim models. We incorporated GP into 2 state-of-the-art attackers. Our main results show significant improvement in the attack effectiveness across all datasets and all victim models. These improvements are consistent for 2 attackers enhanced by GP. It is worth noting that our GP-enhanced attackers even outperform the original attackers with double retraining epochs. Moreover, DPA to DLGP achieves the improved performance while reducing the time cost compared to DPA to DL double. This highlights GP's ability to enhance both the effectiveness and the efficiency for poisoning attacks. To validate our approach, we conduct empirical experiments investigating the gradient similarity between the interacted use item pairs. We found that the gradient similarity between interacted use item pairs is significantly higher than that of the random ones. This suggests that GP can potentially bring additional optimization signals to accelerate the training. We also conducted the surrogate training process. We also studied the surrogate training separately. The results show that the surrogate training trained by GP consistently achieve higher similarity with the victim model on the same training epochs. It accelerates the training of surrogate models, making them more closer to the victim ones. Our hyperparameter analysis demonstrates the optimal threshold and weights for the odd and even layers, confirming the validity of our GP design. Now let's move to the conclusion part. First, we analyzed the retraining process of collaborative filtering models and identifying the cascading dynamic. And based on these insights, we proposed GP by theoretical and intuition to accelerate surrogate retraining and enhance poisoning attacks against recommender systems. Our extensive experiment on 3 datasets demonstrates the effectiveness and efficiency of our approach. Thank you for your attention. I'm happy to answer any questions you may have about our work.
Thank you, Yunfan. Do we have any question from the audience? Because we don't have anything on Slido yet. Okay, I think that's all. Thank you.
Thank you.